Cool. Well, I think we're a couple of minutes after noon, so I think I'll start because I usually do a little bit of an introduction about our company anyways. So if there's people still coming on board, they'll get the important part when we start talking about the actual analyzers themselves and some of their applications. So, we've been doing this this webinar series quite regularly now. We try to do a webinar every couple of weeks about different products. And so this week, I want to talk to you specifically about the Barben oxygen analyzer. So Barben is an Amatec company. And they, along with a few other people, do quench fluorescence based oxygen analyzers. And it has some, both unique properties in how it operates and makes it especially suited to some specific applications. So we're going to talk today mostly about these Barben oxygen analyzers. I usually start off a bit with about who in-situ is. And so I'll go over that. So for those of you who've been on a number of these, good time to grab a tea or something because you've probably seen the first couple of slides already. But then we're going to focus, like I say, on the Barben oxygen analyzers, the measurement principles and how it works, and then look at some applications. So in-situ is a Calgary-based systems integrator and distributor. We operate on the northeast part of Calgary, the 20,000 square foot accessible shop, 9 bay doors, 10-ton overhead crane. We can pick a full shelter up off top of a flatbed and bring it into the building and take it back out on the crane. So we've got great access, to bring equipment in and out. We're an AB 83 compliant fabricator. So for those of you who aren't Canadians, that's probably meaningless. But for those of us in Canada, we have a specific set of requirements and codes around pressure vessels or pressure containing devices. It's somewhat similar to the European Pressure Equipment Directive, but we have a special set of certifications we have to do. Canadian registration numbers, CRNs. And so we're able to manufacture components or systems that meet all the requirements for CRN, and we've done that for Alberta, BC, Ontario, and Saskatchewan. A lot of the folks that are with me here, I've worked with in the past in other companies. So we've brought along a team of people that have a lot of experience in the analyzer business. We have great documentation capabilities. We've done major projects with most of the big engineering companies, Fluor, Worley, Cord, etc. We have a great drafting group, both for solid modeling and for standard like P&ID, 2D type drawings. Our draftsman that's here, one of the draftsmen that's here has been in the analyzer business. He was with Western Research when I started there in '93, just doing analyzer buildings, shelters, and analytical type drafting document packages. Journeyman electrician working here. We do full factory acceptance tests right here in Calgary as well. We have the full capabilities to systems integration, everything from custom design sample systems to integrating process analyzers to doing the PLC and automation side of things to doing full analyzer buildings. We'll take on these projects right from the front-end engineering design perspective. We'll assist and feed specifically for analyzers though. Don't do anything related to process vessels and the like. All of our work is related to analytical measurements, either grab sampling or online process analyzers. And we'll go right from feed through to detailed engineering design, through fabrication, field commissioning, and imperative to us is the ability to service all of our equipment. So, COVID has made it a little bit tougher, but our policy is that if we're going to represent and sell a product, we're going to get our service technicians. We run service out of Grand Prairie, Edmonton, and Calgary, and we're going to get our people down to the factory and get them factory trained. Of course, that has meant more online and Zoom training now than going down to the factories, but hopefully that's changing now. Some of you that know me may know that I also teach the Analyzer Sample System course with Tony Waters, teach that all over the world. That is starting to go all over the world again. I'm, in theory, heading to Holland at the end of the month to teach a 2-day sample system maintenance course and a 5-day process analyzer sample system course, and then to France to teach a process analyzer course. We're doing an online course next week for Asia Pacific. So I get the joy of working my regular day and then teaching from 6 p.m. till 10 p.m. because that's 8 a.m. over in Malaysia. All right, so that's a bit about in-situ and what we do. So we're going to talk today about the Barben OXYvisor, which, as I say, it's got some unique features in terms of its ability to do process analytical measurements of oxygen in a wide variety of process streams. And so we're going to talk a bit about the measurement principle, what some of the benefits of it are, and then some applications where we use it. So first of all, we want to understand why we often want to measure oxygen. When we look at the sort of the big three measurements probably that get done in industry, the big three measurements are probably water, CO2, and oxygen. Probably the three most common things that get measured. And in oxygen, we measure for a number of different reasons. One is that oxygen can contribute a lot to corrosion in systems. And so the presence of oxygen in things like a natural gas pipeline can lead to corrosion of the pipeline materials. And so, this obviously has impacts on capital assets, and that can occur in gas streams, in liquid streams, and even in steam applications. And so, even in liquids, when we're looking at boiler feed waters, we want to know how much water or oxygen is in that boiler feed water. It can affect process efficiencies. It can attack catalysts. It can affect unit operations like amines for H2S and CO2 removal, leading to some of the heat-stable salts that get formed. And also it can affect product quality in streams like methanol and ethanol. And so again, we have specific reasons why we want to measure this oxygen from a process perspective as well. And obviously the other one is that, the thing we talk about when we talk about combustion is that, there's three legs to the stool. There's got to be a combustible material present, there's got to be an ignition source, and in order to get combustion, we have to have oxygen. So it's important for us from a safety perspective in certain streams to know whether there's oxygen there, because it has impacts on whether that stream may in fact become flammable. So the Barben oxygen analyzer is an optical luminescence analyzer. So it uses an optical technique where a beam of light is sent down a fiber optic and into a probe, and the tip of the probe is coated with a lumiphore, a material that will give off light when it's illuminated with another light. So in the case of the Barben oxygen, as I'm going to show on the next slide, we illuminate the luminophore with a blue light and it glows red. And if oxygen is present, it reduces the amount of red light that's given off. So it quenches that luminescence or that fluorescence reaction. So these luminescent O2 analyzers often get used for things like trace levels of oxygen in flare gas applications. And I think that slash was supposed to be pipelines. It's used for oxygen detection in hydrocarbon streams. It can be both gas phase and liquid phase, in nitrogen headers and in tank blanketing applications, and in a variety of different types of process streams. So we're going to give you a whole list of applications at the end. Oxygen detection in liquids, water, methanol, ethanol. Again, anytime we're trying to reduce the amount of dissolved oxygen, it's a very suitable technique for doing dissolved oxygen in liquids. And so we've actually even done an application with Syncrude I think it was Syncrude, to do oxygen dissolved in crude oil because they felt it was leading to some corrosion-based issues. So the kind of the unique features in a nutshell of this is that this technique can be used to measure oxygen concentration in gas phase or in liquid phase applications. It's quite fast responding, typically under 15 seconds. It's poisoning resistant, so we can use it in streams that have high concentrations of H2S or CO2. So some of the common sensors we see, things like electrochemical sensors, are often attacked by acid gases. And so this technology is particularly useful in applications where we're worried about interferences or something attacking other sensors. It's quite sensitive. We go down to single-digit part per million in the gas phase, single-digit parts per billion in the liquid phase. And the device is very nicely packaged. It's a class 1 div 1 explosion-proof housing, user interface on the front that's accessible right through the window. So the touch screen works even though it's in a div 1 packaging. And typically, we'll, in Canada, again, we usually have to worry about if we're going to put things outside about temperature. So we'll often put that analyzer inside of a heated enclosure, put a small sample system and calibration system in front of it. And this can be a complete package that just goes out right out near a flare line or in other applications. I usually mention to people too, anybody who's not familiar with these wind mirrors, I'm really fine if people interrupt me while I'm talking. Actually, I almost prefer it. Questions often are the things that highlight some of the points I perhaps forgot to mention. So feel free if there's any questions. Either you can type them in the chat or just turn on your mic and interrupt me. So the way this fluorescence quenching works is we take a beam of blue light. So we call that the excitation spectrum. Take a beam of blue light from something like a blue LED. We send it down a fiber optic. It hits this luminescent material. The tip of the fiber is coated with a ruthenium complex. And this ruthenium complex, when it gets hit by blue light, it emits red light. So this is what we're using to excite the ruthenium, a blue light source, and we get an emission spectrum that comes out in the red. And so what we do is we send that beam of blue light down. It hits what
do you want?
A lumiphore, and the lumiphore then gives off red lights. For the O2 include application, is optical fouling a concern? How does it overcome the fouling? There's any one of the questions in the chat. Any auto self-cleaning features? There isn't an auto self-cleaning feature. And to be honest, the folks at Syncrude have taken care of that. I think they've been using this mostly in a lab type application, so they can take the probe in and out and clean it. In an online application, yeah, it would certainly potentially be a concern. There's a couple of different versions of this probe. One where the fiber optic probe, one where the lumiphore is actually coated on the end of the fiber, which would be problematic if it gets fouled. But there's a second one where the fiber actually touches up against a luminescent disc, and the disc is really easily replaced. So for applications where we're concerned about fouling or whether there's materials that might attack the lumiphore surface, we usually recommend that second type where the fiber is butted up against a easily replaceable disc. So when we send that beam of blue light down, we get this red emission that comes back. And we have a small photomultiplier tube that's detecting how much red emissions are coming back. If oxygen touches the lumiphore surface, it does what's called fluorescence quenching. It takes that energy, the blue light that had gone in, has added energy into this ruthenium complex. And the ruthenium complex is willing to give off that energy as red light, but if oxygen touches it, it takes some of that energy away. And so when oxygen touches the surface, it reduces the amount of red light that gets emitted. And so we measure the amount of the red light spectra, we can determine how much oxygen is there. In fact, though, there's another method we can use to using the same material to get a more sensitive and more stable measurement. Because the problem with just measuring the how bright the emission spectrum is if the light source itself gets weaker, you'll get less red light back. So you can get more drift if you just measure the intensity of the emissions coming back. So one of the other things that occurs is when oxygen touches the surface, it makes the amount or the signal that's going to come back, it starts to delay it. It decays the ruthenium, or sorry, the emissions coming back gets quenched and decays away faster. And so as a result of that, if we AC modulate the blue light source, we'll get an AC signal that comes back from the emission spectrum. And that AC signal that comes back will start to phase shift as the oxygen concentration changes. So when we AC modulate the excitation wavelength, the fluorescence comes back at the same AC frequency, but it's phase shifted. Because it takes a little bit of time for this luminescence thing to happen. And the more oxygen that's there, the more quickly the luminescence signal decays away, and this causes a phase shift in the signal that comes back. So the more oxygen that's there, the more phase shift that we get. So both phase change and intensity change are proportional or are related to the oxygen concentrations. And so we kind of try to show in the plot up here, that at 0% oxygen, our phase, we have a certain amount of signal that's phase shifted. And as the oxygen concentration goes up, we see that there's a change in kind of the decay pattern of the lumiphore. And that's what we can use to determine the oxygen concentration. Using this AC signal, the amount of phase shift gets us around some of the issues related to fouling, because fouling, again, may make it so we don't get as much light coming back, but it's not going to necessarily affect how the phase shift is happening. And it's also going to help us get around things like drift in the light source itself. So the Barben oxygen analyzers use this phase information as a method to correlate the change in the light intensity or the change in the phase shift to the oxygen concentrations. So, from a hardware perspective, there's a number of features on here. We've got a hazardous area rated enclosure, so suitable for ATEX Zone 1, CSA Class 1 Div 1. The analyzer itself has a touchscreen display. So we've got a full user interface that sits on that screen. It's accessible. The HMI is accessible through right through the glass using some infrared keys. So we have this infrared touchscreen system that allows us to make our way through the menus, do all of the work and servicing on the device itself. We use a junction box at the bottom to connect in the oxygen sensor, the oxygen probe, as you can see, kind of sitting over here. We can bring external temperatures and pressures in as well to do pressure correction, especially because, of course, in gases, the density of the gas changes. And this analyzer is actually measuring the signal that comes out is proportional to the partial pressure of the oxygen that's there. So if you increase the pressure of the sample gas, the partial pressure of the oxygen would increase with it. So pressure correction becomes important if we have a variable pressure of our sample gases. So of course, if we're going to a flare line, we may get back pressure from the flare. So in applications like that pressure correction can be quite important. Some of the key features of this technology is that it's got good long-term stability and quite low drift. The drift increases a little bit as you try to increase the data rate. So the more times you pulse the blue LED, it slowly over time starts to degrade the ruthenium surface. And so higher data rates are going to lead to slightly more drift, but typically we'll see things like, a ppm and baseline drift in a month in the gas phase. Has high accuracy and low detection limits. The limited detection in the aqueous phase is about 1 part per billion. Limited detection in the gas phase, about 0.5 part per million. the probe is detecting the partial pressure, whether even when we consider an aqueous system, it's really the dissolved pressure, the partial pressure of the oxygen in the aqueous phase. And so it's not affected by flow rates. We can have a lot of flow rate variability, and it's not going to affect the readings on this device. It has no cross sensitivity from a lot of the things that may be in some of our samples. I'm not sure, that's a really good question, Randy. So Randy asked, have any customers installed these in SIL rated applications? And I actually don't know. I see SIL come up a lot more for European applications. And of course, I've looked more at North American ones, but we can certainly reach out to the guys at Barben and find that out. I saw JC's on here as well, and he works a lot with the Amatec products. And so I don't know if JC knows that, whether they've done any SIL rated applications with this device. So in the gas phase, some of the common interferences that we see on some other oxygen measurement technologies are interferences from acid gases like CO2, H2S, and sulfur dioxide. And so we can use this analytical method in streams that have very high concentrations of H2S. We did an application with 55% H2S, and there's no impact on the sensor performance or lifetime. It's not affected by pH. It's not affected by various ions in solution, like sulfate ions or chloride ions. In the mining industry, it's not affected by some of the metals that might be present in solution. It's not affected by other gases like hydrogen, combustibles, nitrogen dioxide. And so it's a very interference-free measurement. The one risk with it can be some aromatic hydrocarbons. Good question in there too. It can be affected by some aromatic hydrocarbons, so we have to do a bit of an application review to look at stream composition still, but generally there's very little interferences on the measurement. The replaceable disc is not actually a reflective mirror. If you actually look at the disc, it's a piece of rubber with this ruthenium coating on it. And so it in itself is not affected by interferences as well. And there's very little, it's all a question of, again, picking the right polymers so that you can be sure that it's compatible with the stream. From an installation perspective, it's quite simple. We don't have to do very much sample conditioning. How often does the coating need to be replaced? Again, a little bit applications dependent. If it's a really clean application, like a natural gas application, that these probes will last for a couple of years. If you've got an application that has a material that might attack the polymer base or the ruthenium coating, you're going to replace them more often. So we have a particularly difficult gas phase application where there is some materials that would attack the surface. And so what we've done is put a very light Teflon coating. Hi, Madeline. No SIL, thank you. Didn't know you were on. Oh, it was a direct message to me. Sorry, just announced her out there. So in this one application, we put a Teflon overcoat, a very thin Teflon overcoat over top of the polymer material and the ruthenium coating, and that provides some protection against other materials, and oxygen diffuses through the Teflon really easily. It does slow down the response a little bit, but again, you still get fast response, and it puts a protective layer on that coating. Very little need for sample conditions. One of the beauties of this device, there's a couple things I used to do live. I have customers in, I'll do some live demonstrations sometimes. I'll take the sensor and put it into a T. So I can have, say, nitrogen with 100 parts per million of oxygen flowing through it. The analyzer is reading 100 parts per million. Pull the sensor out, expose it to room air. A lot of oxygen analyzers, if they get exposed to air and get saturated, they take a long time to respond again. So the interesting thing with this demo is you put the probe in something like a Teflon ferrule. So you can just loosen the ferrule a bit, pull the probe out, expose it to air. Analyzer's pegged. It's at 209,000 parts per million, or 20.9%. Put it back into the T, and within a minute, you can be right back down to reading 100 ppm again. The other thing I'll do is I'll take the probe out and dip it in a glass of water. So the probe's wet, because one of the things we worry about in our analyzers is if we get water carryover, liquids carryover. So I'll purposely wet the tip of the probe, give it a little shake, dab it against my shirt, put it back into the tea. Now, once enough nitrogen is flowed by to dry out any liquid that's left on the surface, it goes back to reading the gas phase concentrations just fine. So again, the whole device has hazardous area approvals. We don't require things like special permeable membranes. Typically, I did mention we did put a Teflon membrane on some. We don't require really precise temperature controls, although it does impact, we measure the temperature, so we have to do an ideal gas law correction for gases. There's not electrolytes in there, like an electrolytic type oxygen sensor. Generally, if these fail, they'll inherently fail high. What'll typically happen is there's either, for some reason, the material no longer fluoresces because it's been damaged, or the LEDs died, you don't get any fluorescent signal. So inherently, they will fail high. So you're not going to be in one of these positions. What can happen with some other sensors is they'll fail low. So you'll think that your system has very low oxygen concentrations and it's safe to keep running your process. But in fact, because the sensor fails low, you end up with this bias reading that puts you in the position where you can do the most damage to your process. So having it fail high is a beneficial thing to do because it means you're going to probably shut in or certainly go out to try to inspect and see, is there really high oxygen in my concentrate in my application? A typical installation we might do up here for a gas phase application, this is to put in a small flow panel, which allows us to do calibrations or validations of the readings, online measurement of the process fluid. Again, if it's going to be going up in Canada, we're going to want to put this inside of a heated enclosure. So, we can build a small sample system box, about 1 meter by 1 meter, and mount this right out near the process application. And so this would be, you might go on something like a flare gas application or on a vapor recovery unit. So from an applications perspective, we'll touch on a few of them. There's a number of application notes up on the Barben site, and we're actually going to, for those of you who've been on these before, we usually do a mail out afterwards with, here's a copy of the slides, and we're going to add some of the application notes in with that as well. So one of the places where we see these get used a lot is in natural gas processing, especially if we're doing something, pulling up some low pressure gases. So if we've got say we're drilling oil wells in the Bakken and we've got low pressure casing gas that we have to compress to push into our natural gas processing plant. Well, that field compressor station, if it gets any leaks in its seals, you're potentially going to add oxygen, have oxygen ingress in there. And adding oxygen into those streams, especially into a wet natural gas stream, can potentially cause corrosion into the in the pipeline materials. And when it gets into the gas plant itself, the oxygen can cause problems with glycol. It can cause problem with our amine stripping systems. And so we want to be able to detect if we get any leaks on any of these compressors. If we've got multiple wellheads, we wanted to look for leaks on these compressor seals. And we do that by looking for oxygen in the produced fluids. Again, kind of figured Barben is suggesting to have one before and after the compressor. We don't typically see people do that. We usually see people measure after the compressor, so we know if anything has managed to leak in through seals in the compressor. There's also a specification for O2 and pipeline gas. And so when we're going to have gas going out the pipeline, we potentially want to have that O2 measurement there so we can determine if the natural gas is on specification. Canada has a much higher O2 and pipeline gas specification than the US does. So we see a lot more of this measurement go on in the US because there the typical range is 100 parts per million. Here we're allowed to have up to 4,000 parts per million. So really we see this O2 and natural gas application kind of driven by the US side of the business. But there's a number of other applications where this comes into play. And a lot of these applications will revolve around this idea of having compression going on. As soon as we have a compressor or a pump, we have a potential for leaks around seals. And this means that once those seals start to leak, we can get oxygen ingress mixed with the hydrocarbons. And like we said, this can lead to corrosion issues. It leads to safety issues. It may damage upstream catalysts or reaction fluids, like things like amine. So one of the applications that we will commonly see, and we're just doing one of these up in northern Alberta, is in vapor recovery units. So if we've got something like a condensate stabilizer or any kind of hydrocarbon processing facility, we may have some low pressure gases that come off of the overheads of a tower, for example, and have to be compressed before they can either get put further upstream in the plant or put to sales gas. And so we want to be able to determine whether there's been any oxygen ingress into that system. And so again, we see sitting right here, we've got our compressor, right? So we put vapor recovery units in to capture volatile organic compounds and prevent them from venting into the atmosphere. And we'll even put these on top of, say, storage tanks. So for example, in northern Alberta, they'll put bitumen in a tank and they might blanket it with sales gas, with methane, keep the oxygen away so it can't combust. Now we're in a situation now, if any oxygen gets in there though, we've got a combustible mixture. So we'll see these in any application where there's tank blanketing or any other type of vapor recovery off the headers of vessels, off the headers of contactors. We want to be able to capture that vapor, pressurize it, and put it further upstream in the process. So we want to measure the oxygen that's there, because if there's acid gases present, especially H2S and carbon dioxide, additional oxygen can dramatically increase the rates of corrosion. So we want to concern ourselves about corrosion limits, and we also want to concern ourselves about flammability. So some of the advantages that Barben brings to this is that when we're trying to do trace oxygen in these, so typical range might be, say, 0 to 300 ppm. One of the established and existing technologies is to use electrochemical cells. But those cells are often poisoned by things like H2S and carbon dioxide. And when they are, they fill low. So there's been a number of pipeline-related issues where those type of oxygen sensors, and because they fill low, has led to damage in processing vessels and damage in the pipeline themselves. Try to get around those higher concentrations. We're looking like at thousands of ppm. Paramagnetic sensors and tunable diode lasers work well. However, they usually don't have that low single-digit parts per million detection limits. And so what it means is you don't start to see a leak in the compressor seal until the concentrations already are getting fairly high. And so you may have already created a lot of corrosion issues for yourself. So one of the advantages of the Barben is that we can do very low detection limits. Typically, we can, in that sort of 1 ppm kind of detection limit, 1 ppm, half a ppm detection LOD, and measuring reliably in the 10, 20 parts per million. And so we can get these low concentration measurements that are difficult to do with some of the other technologies. Also, if, as I mentioned, I can dip it in a glass of water and put it back to measuring. So if we do have a system where we have risk of liquids carryover, whether they're hydrocarbon liquids or water, the sensor can be fairly resistant to those and not damaged by those. Whereas if we get liquids into the cell of a paramagnetic analyzer or into the cell of a TDL, they will cause a lot of problems with the measurement and fouling on the optics in a TDL, fouling of the surfaces on the paramag. And generally this technology is less expensive than putting a TDL in to do it. So there's a number of other applications though, and especially, I wanted to focus a little bit because, we hear so much about global warming, carbon dioxide emissions, methane emissions to the atmosphere, et cetera. And so I wanted to focus a little bit on some of these applications where this technology can be used as part of a system to mitigate emissions from gas processing or emissions from combustion sources. So one of the first ones I'll just mention is acid gas reinjection. We used to see a lot of times as people started processing natural gas, they would build a sulfur recovery unit in order to remove the H2S and process that H2S in a sulfur plant. For smaller facilities, and it's a much easier to get a permit because when you have sulfur, if you're going to convert the H2S to elemental sulfur, it involves a combustion process, it involves stack gas emissions, so we typically have SO2 emissions with that, and there's CO2 emissions that go along with the acid gas side. So we can achieve the same goal, use an amine unit to remove CO2 and H2S from the product natural gas, whether it's casing gas or whether it's natural gas from a natural gas well. So we can sweeten the stream with amine, take the H2S and CO2 out, compress it, and push it back down into the reservoir. This has a couple of effects for us. One is it means we don't have any emissions of those species because we've taken them, compressed them, and pushed them back down the reservoir. And second, it helps us to repressurize or keep pressure in the reservoir. So we'll see this being referred to as EOR, an enhanced oil recovery method. So acid gas reinjection can allow us to help to repressurize or increase the pressures in the reservoirs and mitigate some of the greenhouse gas emissions. They generally have lower energy requirements than putting a full SRU in. It's scalable for small plants or big plants, lower capital costs than putting a full SRU in. And certainly in Canada, it has become a lot easier to get an acid gas reinjection site permitted than to build a new sulfur plant. So, so the general process, if you like, looks like something like this, where we have some sour gas that may be both H2S and CO2 laden. There'll be a gas sweetening unit, typically an amine unit that will remove both some of the H2S and at least some of the CO2. On the flash or low pressure side of that, we'll generate this acid gas that we can now take into a compressor system, recompress it, so acid gas compression pump, push it through a pipeline and put it back into an injection well. Now, we may have to dehydrate that. We usually do have to dehydrate that because the gas that comes off that amine contactor is often water saturated. And if it's at low pressure and water saturated, when we try to increase the pressure, we're going to hit water dew points. So often between separate stages of compression, there'll also be a dehydration system. And so, when we're looking at these, when we're looking at doing an acid gas reinjection type application, the common things we're going to want to measure are the water dew points and the oxygen contents. So we can use the Barben here for the oxygen content. The important piece of measuring that oxygen is once we've taken that up to pressure, we want to try to prevent corrosion in the pipeline. And we also don't want oxygen, if we are using this as part of enhanced oil recovery, we don't want oxygen going down in the reservoir because it's going to create additional issues with potential oxidation of materials along well bores and inside the formation itself. So again, the Barben has the advantage of being able to do the trace oxygen measurements. It's quite resistant to liquid carryovers, not poisoned by the H2S, not poisoned by the CO2. Again, if we're going to just do LELs, paramags work fine, but because of issues like potentials for liquid carryover, we really want to look at devices that are going to be resistant to those liquid carryovers and allow us to detect at soon as we start to get a leak in any of the pump seals, allows us to determine that we've actually got a leak in the pump and we better start thinking about scheduling maintenance. So, we often think about this when we think about acid gas reinjection, especially up here in Canada, we're thinking about H2S primarily, or H2S and CO2. By the way, I should also mention, this picture is from Compass Compression here in Calgary. I did take the picture off of their site without getting permission, so I should mention it. This is a Compass Compression acid gas reinjection compressor skid. So we often, like I said, we often think about this as being a way to take H2S out of the natural gas and put it back down into a reservoir, get rid of it in some way that we don't have to further process it. But this is also becoming really big now with this whole greenhouse gas concerns that are going on, because we're seeing a lot of people now talk about carbon capture and utilize carbon capture, either for the carbon be utilized to be part of a chemical process someplace, or used as bottling grade CO2. And Wolf Midstream runs the Alberta Carbon Trunk, brings a big CO2 pipeline that brings CO2 down from Fort Mac down into Edmonton. And some of that is used for processing, upstream processing as well. So we have carbon capture where it's either utilized for another application or it's put in the storage someplace. And we can apply this to natural gas wells. We can apply this to the energy that is being used, let's say, in steam generation at a SAGD facility. But we can also apply this directly even to things like stacks. Any place where there's high concentrations of carbon dioxide, we can use a carbon capture method like an amine, take that carbon dioxide out of the gas, recompress it, and push it back down into a wellbore. So the typical approach to this has been to go to inject it down. If we are doing the storage part, we look for a depleted reservoir, because these things can trap a lot of CO2. They can hold, there's a large volume reservoir underground, and if it was a natural gas reservoir, it's held natural gas in it for millions of years. And so the reservoirs themselves are proven traps. They're known to hold oil and gas in them for millions and millions of years. So if we can inject the CO2 and push it back down the reservoir, we can effectively permanently remove that CO2 from as being part of any of our emissions. So it's a very well-established technology. Again, we've done a lot of this acid gas reinjection, get rid of H2S, take that same technology, push it down into you push carbon dioxide down into a reservoir, and now we can capture that carbon dioxide in and prevent the greenhouse gas emissions. If that reservoir is still in production, it can also, that CO2 can be used as a enhanced oil recovery methodology as well. And so the figure down here at the bottom, sorry, it's a little bit small probably to see, just gives you an idea of how much more we've been doing carbon capture and what industries are primarily using it. So you can see that we started doing carbon capture as early back as the 1980s. Substantial increase in the amount of carbon capture that was done occurred in the 1990s. Didn't increase that quickly through 2000, 2010, but by 2020 now, with the increased focus on GHGs, we've seen a large increase in the number. The y-axis over here is the number of million tons being captured and either put to storage or utilized. And the primary industry that you can see that's doing this, shown there in the light blue, is natural gas processing. And again, Alberta, both Alberta and Saskatchewan have some fairly large carbon capture demonstration projects that have either been running for, some of them have been running a long time, and there's a lot of new ones coming on board as well. So we want to measure oxygen in these again, though, because of the fact that oxygen is going to contribute to the potential for corrosion. And so we want to look at putting an oxygen analyzer in that can deal with the issues that can come up with compression, the fact that we may get leaks across the seals, we may hit some dew points occasionally. And so we look at something like the Barben as a methodology to measure the amount of oxygen in that CO2 stream. Again, interference free from CO2, doesn't get poisoned like an electrochemical cell. And so we can use this technology to measure low concentrations of CO2 in relatively pure carbon dioxide. I realize I don't think I put a slide in about flare lines, but I meant to put a slide in about flare lines. Similar to the vapor recovery side of things, though, did I not? Yeah, I forgot a slide. Huh. Should have been right here before this one, but anyways, so I'll just mention it. Another place where we see these oxygen analyzers getting a lot of use is in flare gas. You know, in a refinery or a petrochemical plant or a gas processing facility, we often have some vent gases that are often hydrocarbon laden that we allow to go to the flare stack. And what we don't want to have is significant amounts of oxygen get into that flare line. Because if we do, we have the potential for flame to propagate back up that way. And so we want to measure and ensure that we're not getting oxygen in our flare lines. And again, flares are low pressure. There's often pumps that are pushing or compression that's going on to push material into there. So there's a potential for oxygen ingress. And we often have these lines connected to vessels that sometimes get steamed out. So the sample systems themselves or the lines themselves can often have a lot of liquids in them or condensables in them. So all of those features of the Barben, the fact that it can deal with condensables, measure low concentrations of oxygen, poison resistant, very applicable to flare lines as well, because again, we'll often see a lot of H2S in flares too. So another application that's coming up, again, on this green energy side of things is alternative methods of making methane. And we see this as being, as referred to as biogas. People will call it landfill gas. The basic idea is that we have some kind of a reservoir or vessel, maybe a vessel is kind of built into the ground, or it may be an actual wet digester. We take some material and we let it essentially, let the bacteria there digest that material. And if that's done in an oxygen reduced environment, it will tend to take a lot of the hydrocarbons that are there and make them into methane. So it might be manure, it might be some other solid waste, it could be the refuse in a landfill. And if we go to a landfill and had a sensitive methane detector, you'd realize that there's methane just coming off the ground from the processes that are going on underneath the ground. We see it in swamps too. You'll see these bubbles rise. They're often H2S. They'll often smell sour, like rotten eggs, because there's sulfur species in the swamp as well. So in this whole digestion process, it's taking sulfurs and making them into H2S, taking hydrocarbons, digesting them down to methane. And we can take that methane that comes out and actually use it as a source of fuel for, a gas turbine, or we can use it and put it into pipelines. And so we'll see people now, there's thousands of landfill and digester type applications in North America right now, where they're taking material, allowing it essentially to rot in a oxygen-free environment, making that creates methane, and they want to compress that methane and put it to pipeline. However, because of the process, with dilbit streams attack the coating, Harvey, that's probably I suspect you would have issues in dilbit. Usually has a pretty high aromatic content. And this tends to be the aromatics that attack those coatings. It wouldn't be like if someone's been doing the dilution side and has been using butane or a condi that doesn't have a really high aromatic content, it probably wouldn't be as much of an issue. But I think if there's high aromatics, so that's usually where we have problems. So on the landfill gas side, as it gets close to the surface, there's more oxygen and nitrogen air in there. So you'll have elevated concentrations of nitrogen and oxygen typically in the methane that comes off a landfill. And the stream that is produced because of the oxygen that's there, because of other processes that are going on, aerobic digestion makes carbon dioxide. So the streams that come off of a landfill, the raw gas coming off now, landfill often has high levels of CO2 in addition with the methane. So they end up having to typically take that gas, scrub the CO2, often done with an amine, and amines don't like to see a lot of oxygen. And so before it's contacted with the amine, it's usually compressed. So we kind of show a little bit of the process over here where we have a digester running through some dryers to take the moisture out before we get into the compression stage, because we don't want water condensing out in our compressor. So we dry the stream first and then compress it. And it's after that compression where especially we're concerned about O2 levels. Because again, any leaks in that compressor is going to lead to oxygen getting into the stream. So because the landfills tend to produce low pressure gas, they need a compression stage before they can get into pipeline. And that compressor leak is a potential issue. We also want to be measuring here because they do have higher levels of oxygen. It is more likely that landfill gas will exceed the oxygen allowances for the tariffs for a natural gas pipeline. So pipelines have specifications on the amount of oxygen that's allowed into them, often related to oxygen the impact of oxygen corrosion processes. And so we want to get that oxygen measurement before we put it into our natural gas pipeline. So again, the advantage of the Barben here is things like H2S that comes from these digesters or landfills will not affect the analyzer, nor does CO2 affect it. So we can use it in high H2S and CO2 streams. And again, these are pretty low maintenance devices. There are no moving parts. You periodically have to potentially replace the sensor, but it's a one-part replacement and you're back up and running again. So I touched on just some specific applications that were more related to kind of, greenhouse gas emissions and some of the information that we see a lot in the news these days. We have a whole slide here and we'll send this out to you. There's a whole bunch of places where people want to measure oxygen and where these analyzers are particularly useful. For the refining and petrochem guys, Mirox units, things where we're separating mercaptans. Again, we worry about oxygen getting into those systems. We've seen these analyzers get used in those applications a lot. Anytime we're doing natural gas processing, we're worried about oxygen in our natural gas, so gas plant inlets and outlets, custody transfers and metering stations, pipelining. On the upstream side, if we're doing acid gas reinjection or enhanced oil recovery, we have boosters or compressor stations. All of those are potential places for oxygen ingress. Offshore and even onshore oil and gas, when we're looking at produced waters, if we're looking at things like using waters to go into a boiler, say in a SAGD application, we want to know how much oxygen is dissolved in our water. And so we can use the same sensor, the same technology, both for gas phase and for liquid phase applications. Similarly, again, in the refining and petrochemical side, numbers of tank blanketing type applications. If we're worried about our oxygen sensor potentially getting poisoned out, and if we want to get that ppm sort of sensitivity, it's an ideal analyzer to use in these tank blanketing type applications. So that kind of wraps me up about the Barben. I usually throw a slide in here just mentioning some of the other product lines that Insight deals with. Oh, sorry, I got a question come up here a little long and I got to read it now. Regarding competing technology, do you have any thoughts on the TDL laser sourcing predicament? We discussed this with one of our TDL laser analyzer suppliers who indicate the telecom industry lasers have long been used in design of TDL analyzers. Laser costs are relatively inexpensive due to large scale production. Telecom industry has now changed their laser design format, and their new design is incompatible for use in TDL analyzers. So it appears to be no new TDL analyzers installations until this is resolved, probably resulting in higher cost TDL lasers. That's a pretty interesting thing, Randy. I was not aware that that was currently creating issues with the TDL market. A lot of the TDLs that I see, certainly for, like oxygen is a different one to do by TDL, right? O2 is even when we do it with a TDL, it's a visible laser right on the edge of the red spectrum, 760 nanometers. it's actually because of that potential kind of transition that oxygen can quench the fluorescence. You notice that we get a fluorescent signal in the red, and oxygen quenches it because 760 nanometers is right in the red, and that's where it pulls the energy away. So these ones were typically the 760 nanometer lasers, as far as I know, were never used as in the telecom industry. However, a lot of the other things that we do, when we talk about moisture or we talk about H2S, sorry, the place it doesn't want to let me write on my screen. We'll often see lasers up in the, especially moisture. I think it's about a 1540 nanometer was a common wavelength for doing moisture. And that's right around the 1550 telecom lasers. Oops. So a lot of the TDLs that were used for moisture measurements, especially the early ones, they were kind of, some of the lasers they used were almost the cast-offs from when someone was trying to make a 1550 nanometer laser. And so I actually got one that lasers more at 1540, didn't do my doping right when I was making my semiconductors. And they ended up being that they could take those lasers and use them for doing laser spectroscopy. However, what we've started to see is, companies like NanoPlus and Iblana, custom making. They do a lot of custom lasers for TDL applications in those 1800 nanometer regions, 1800 nanometers, 2300 nanometers, for doing things like H2S or CO2. So those lasers, I would imagine there's not going to be a big sourcing issue because they are often custom made specifically for TDL applications. But it's interesting. I got to look into this change in the laser design format because often when we talk about tunable diode lasers, we talk about DFB lasers, and I didn't realize they'd gone away from maybe using DFBs as part of the telecoms thing. So thanks for bringing that up. Give me something to Google today. So again, we just like to mention, we have a number of different partners. We've just recently brought on UWT for a bunch of level control devices, but we work with Extrel, with Atom, with Mark Metrics for Ramon. A big product line for us is JP3 and their near infrared analyzers. And we have a number of products. If any of you were on my, from Paul, good question too. If you were in the last webinar we talked about a lot about some of the products that we make, like sample system components, automated samplers, etc. Thanks, Rennie. Please do keep me posted. So Paul asked a question as well. T90. T90 is typically about 15 seconds for these. What's the trigger to know the sensor degradation? Is it the slow response? No, typically it is just that we typically recommend that you run a zero gas, like run a UHP nitrogen on it, say once a week or so, and look to see whether it's coming right down to zero. The thing to know that the sensor is degrading is usually zero drift. That's the biggest sign that we often see. Because as the lumiphore gets depleted, whether it's because of chemical attack or from seeing too much blue light, it doesn't fluoresce as much, and the amount of phase change you see changes. And so we get zero drift over time. If there's a lot of zero drift, it's usually a sign that the lumiphore is being attacked. To wrap up, I always usually like to put aside just to show a bunch of the systems that we've integrated, everything from composite samplers. I think it just animates through a bunch here now. Composite samplers in little shelters and buildings on pipelines, automated grab samplers with near infrared analyzers, PLC integration with sample system integration, solvent flushes for sample systems to clean filters and cells. If we're worried about windows getting contaminated, we can put a solvent flush in, automatically clean it. We do a fair bit on this automated grab sampling thing. Another composite sampler, I think that one's out at NWR, and shelters with. Sir, I can't hear you. If you're talking to me, I can't hear you. Oh, there it goes. Screws off. Oh, sorry, my screen behind me went off too. I love this shelter because it's got two of our composite samplers in it. You know, composite samplers here and here. That solvent flush system, PLC controls, near infrared cell, automated sampling panel, etc. So it's a photo one of my service guys took out in the field, and just I always like to show that one as kind of one that we wrap up with. So if you need any more information, please feel free to contact us. Scott is usually on here, but there's a Gas Processing Association golf event going on today. So Scott's out there with some clients, but you can feel free to reach out to Scott Galenza or myself. Check out the information on our website. Of course, check out the information on AMETEK website. And usually all the things that we're doing, we try to post up on LinkedIn. So feel free to follow us on LinkedIn as well. So a couple of minutes over, but thanks very much for your time. If there's any other questions, happy to deal with them.